Hello, can you hear me? Okay, thank you. So I can start anytime you want.
Just a few minutes, please, Mr. Bennis.
Okay, sure.
Thank you.
Get some water.
Okay. Okay, so hello everyone.
You can see me after. Yes, I'm here.
Okay, thank you. So good afternoon, everyone, and welcome to this first afternoon of the first day of our conference, ECSSD. It is with a great honor that I introduce Professor Mehdi Bennis, our second keynote speaker, who will give us a presentation titled Communication Efficient and Distributed ML, Machine Learning, over Wireless Networks. So Professor Bennis is full professor at the Center for Wireless Communications at the University of Oulu, Finland, and an Academy of Finland Research Fellow and head of the Intelligent Connectivity and Network System Group. His main research interests include radio resource management, heterogeneous networks, game theory, and machine learning in 5G networks and beyond. He has co-authored one book and published more than 200 research papers in international conferences, journals, and book chapters. He has been the recipient of several prestigious awards, including the 2015 Fred W. Ellersick Prize for the I3E Communications Society, and in 2012, Professor Bennis received the I3E ComSoc Radio Communications Committee Early Achievement Award. Professor Bennis is a I3E fellow. Sorry. So, Professor Bennis, the floor is yours for the presentation. Thank you.
Thank you very much. Sorry for the long bio. Okay, very good. Can you hear me well, right? Hello, can you hear me?
Yes, we can.
Okay, perfect. So I can get started. So I have 1 hour, right? That's my slot. So I'll probably just finish a bit before for question and answers. Is that okay?
Yes. Yes.
Okay, perfect. Okay, great. So thanks a lot again for this invitation to deliver a keynote today with you all. So the title is, as was mentioned, is going to be about communication efficient and distributed machine learning for and over wireless, and I'll explain to you why I'm using this connotation here. Everything else has been said, and let's get started. So the outline today will be about, first, motivation, a bit about the topic of Edge AI, which is a very, very, very trendy topic in both machine learning society, but also, of course, wireless community, in the advent of course, 5G and beyond 5G, 6G. So I'll motivate this a bit, and then I'll delve into a number of techniques and enablers that some of which you are already familiar with, and then I'll show you how to apply these techniques in a variety of problems, keeping in mind that, of course, my talk today is really to motivate you and provide for you a framework so that you can apply it to solve your own problems. Okay, and then I conclude the talk. All right, so quick motivation. So of course, we are in 2021. Of course, again, as I said, we are living now in a beyond 5G, 6G era. And what really characterizes this generation of wireless system essentially is a number of things. So first of all, there is this number of new applications, XR, VR, autonomous driving, of course, referred to as mission critical applications, which typically cannot be operated with centralized and best effort machine learning. Okay, because again, these are safety critical applications where decisions have to be made on the device. Okay, so typically these devices have to train machine learning models either directly by communicating with other devices. So devices here could be for you vehicles, base stations, sensors, robotic arms, whatever you have in mind. Okay, so therefore these devices need to train this model by communicating directly with other devices, right? Or by using a server or a base station to do that. Now, there are a number of constraints, of course. So in wireless communication, we are familiar with the notion of course, the channel is dynamic. It's changing over time and space. Bandwidth is typically limited, right? It's scarce. And then we have, of course, all sorts of kind of dynamics, interference, noise, right? On the other hand, we are also facing a number of constraints on the machine learning side, namely that now we are talking about small data paradigm, moving away from the big data, paradigm of Google and Facebook and others, right? Small data paradigm, and of course we have constraints in terms of resources. So resources here means memory, storage, compute, bandwidth, right? And then we're dealing, of course, with also a kind of new phenomena in the sense that now the data distribution is no longer centralized and IID, so independently and identically distributed, but non-IID. And this kind of heterogeneity gives rise to a number of problems, which I'll explain to you later. So just to summarize, so here what we are talking about is kind of a marriage between machine learning on one hand and wireless communication on the other hand. And this is now giving to this, or gives rise to this very nice co-design of machine learning and communication. And of course, what we are now facing is essentially solving two problems, two overarching problems. So the first one is, how do you train now machine learning models in a communication efficient, privacy preserving, fast, reliable manner, right? For the training, the inference, of course, or the prediction, but also the control. So in the reinforcement learning domain, which is essentially the same as saying control, right? How can we do the same thing as we did before in the centralized case, meaning having one entity with a lot of data towards distributing completely this data across devices and training model. Number two is machine learning aided ultra reliable communication. Essentially, this is basically saying that how do you use machine learning models to help you communicate better when you do not have access to a model. Okay, and I'll come back to this a bit later. Now, traditionally, of course, I hope everybody knows, so classical AI is essentially depicted here on the left-hand side. So you have, of course, a server with all the horsepower that you can imagine. Think of it as a data center. Then you have a number of devices here, okay? And these devices typically generate data at the edge on the device. And then what they used to do, at least, is to communicate this private data, raw data over wireless to the cloud, and then the cloud trains this model. So this is obviously terrible in terms of privacy, terrible in terms of bandwidth efficiency or latency or delay, horrible in bandwidth. Okay, but this is how things used to be. Now in 2017, Google basically came up with this very nice intuitive idea of federated learning. Here the idea is as follows. So instead of now communicating the raw private data from the device to the server, what you end up doing now is communicating a model, right? This is similar to saying use your gradient descent algorithm or stochastic gradient descent algorithm and communicate the model updates or the gradients instead of communicating the entire raw data. Okay. As a result, this is now, of course, privacy preserving, right? It's bandwidth efficient because you're communicating much less data in size, and you're still using the cloud, but now to just average, we'll aggregate models from all these devices, all right? In other words, sharing the experience from all these devices to kind of improve the training or inference at the device side. And of course, now you can push this further when you get rid of the server. Let's say you want to do this now collectively among robotic arms, sensors, drones, cameras, whatever you have in mind. So you inherit not only this idea of federated learning, but you also kind of do this in a completely distributed manner, meaning that now, of course, if you are very far from the base station, there's no point to communicate your model, to the base station. You can communicate with, here, you can see it here, the nearest neighbors, right? This is essentially the where things are today, right? Now, because of course my talk will be a bit technical, so I'm going to use this kind of picture to guide me through the talk today. So what I have done is I have divided this kind of a zoo of algorithms in terms of three families. So there's the first family here, which is referred to as the model parameter exchange. So here the idea is that devices will be communicating the entire models, okay, to the server, exactly as federated learning does, okay, to solve a variety of problems. So sometimes, of course, you're concerned with the scalability, sometimes your robustness of a model, sometimes you want to have an adaptive model to the channel or to other dynamics. Then I'll talk about the second family, which is referred to as the model output, which is a better family of algorithm in the sense that now, instead of communicating the entire model, I think of this as, hundreds or thousands or millions of parameters that are communicating over the air. Now the idea is that we can compress this model and communicate what we call a logit. Logit here, this is what you see here. This is what gets communicated. So we came up with a very nice idea in 2000, maybe 18 or 19, called federated distillation, which I will present to you later. And then there is a third family, which is referred to as surrogate data exchange. So here the idea, think of it, is just taking a piece of text, right, and just compressing that text, extracting a summary, and there's a summary that you will use now to carry a task. Again, it could be training, prediction, control, whatever you have in mind. Okay, very good. So let me get started now with federated learning. Okay. So before I start, just a timeline for some of you. Federated learning is one of the hottest technique now or tool in the society. But for those who don't know, so 2017 was the first paper by Google. Then they organized a workshop in 2019. This is where actually I was invited to kind of present my view of wireless federated learning, because obviously Google does not care about wireless. So in some sense, they are now, of course, trying to see how to combine both communication and machine learning, because you have to do it. You cannot abstract communication. You can actually exploit it to have a better and more robust training. Then, of course, the number of publications has really skyrocketed here. This is an exponential trend. Which begs the question whether this trend will continue to go up, or we will really start to see some kind of diminishing return. I guess only time will tell. All right, so what's federated learning? In very short, this is about having a number of, devices here, which you see here, right? Every device has access to a number of training data samples with labeled data. In this case, I'm focusing on a supervised learning problem. And then, of course, you have a server here. And then what you want to do is train a model. So what do? You can write this down mathematically, which comes down to writing a kind of a minimization of empirical loss here, right? F, across number of workers. And then this is the kind of global model, right, theta here, and this is now the local model of the worker or the device. And you basically just want to minimize this loss function, which could be convex, non-convex, right? And this is a kind of very straightforward problem, because what you end up doing at the server, again, you just average this gradient here, right? This is a sum of all the gradients, and then you send this back to the device, and you iterate this back and forth until you converge to some sort of point, right? Now, this is easy, again, as I said, so things get a bit tricky when you have this kind of non-IID-ness, as I told you before, because now, of course, these devices have different number of classes, right? They have different number of samples, say from, very rare classes, right? So, of course, if you train, clients, in this case, it will end up basically hurting the performance, in the sense that now, if you have, because the server gives you only a global model. So now if you have a global model, in some sense, every device is trying to pull the model toward its own local data. Another device is doing it on the other extreme. So you end up with a kind of unfairness in terms of the model. But this is essentially where federated learning started. And there has been some research or papers that have shown, actually, if you plot the test accuracy as a number of communication rounds for a number of IID and non-IID settings, you can see the significant drop here in terms of performance once you go from IID to non-IID. And this, of course, makes, again, a lot of sense, which says that actually maybe we need to now cluster devices together before we can train them. Don't train just any type of devices together, because it will end up hurting the performance. Okay, this was done on an MNIST data set, and this is the CyPAR10. But this is a kind of universal kind of result in some sense. So back in 2018, we basically, when federated learning was not that famous, we used this technique in the context of 5G. And here, what you have here, we have a context of vehicular communication. You have vehicles here, and these vehicles need to minimize transmit power from one vehicle to another, and their latency because we were basically interested in this ultra reliable communication, which is basically the kind of the defining feature of 5G compared to 4G, right? So now if we want to do this, the problem is the device doesn't have access to this distribution. This is, think of it as a network-wide latency, right? It's a latency distribution across the network. So the vehicle has no way to access this distribution. Therefore, it cannot solve the problem. Now, to solve this problem, you can do it in many different ways. You could do, in kind of Google way. You could, meaning in a centralized case, meaning that the device now, has this data here, data samples, communicate into the server, right? And then the server maybe, trains a model. But we are not interested in this regime because we are really in this kind of ultra reliable setting where we need to do this under constraints. Okay, this is why we have this kind of tail distribution here, which is the latency wide distribution, right? And we are really trying to actually estimate the distribution from data. Now, this gives rise to this kind of GPD distribution here, which comes from extreme value theory. Branch in statistics, right? And here what we want to do is really apply principles of federated learning, meaning that now we want that vehicles do not communicate their samples. We want them to communicate just these two parameters here, which are referred to as the shape and scale, which are actually coming from these models, this family of distributions, right? Which is again referred to here as the generalized Pareto distribution, right? In other words, our problem is somehow simpler because we just need to estimate from data using a maximum likelihood criterion, right? These parameters here that you see here, right? The scale and the shape of this distribution. And we want to do it, of course, in a privacy-preserving manner, bandwidth efficient manner, and we just use federated learning, right? That's actually what we did. Now what you can show here, kind of compare the proposed approach, which is this extreme value federated learning approach versus centralized. So centralized means that all the vehicles communicate their data sample, okay, versus ours using federated learning. So as you can see here, actually we can achieve the same reliability, right, in orange, as a centralized setting, while communicating much less, right? Here, this is the gap here. So this is our approach. We communicate much less, right, compared to the centralized approach. Why? Of course, is because we don't communicate the raw data, right? We communicate the model. Now, this gain could be actually much bigger if you were talking about communicating images, right? Think of this as now as an autonomous vehicle, right? Which has a high definition map, and that's what you compress now and communicate to the server, right? Here we are actually in a safety scenario, meaning this vehicle has to communicate very few. I mean, the payload is very small. Okay. Now, once you think a bit about this federated learning idea from Google, right, with one server and workers, you realize really quickly that whether we could do this in a much smarter way, right? So the answer, of course, is yes. So what if now we kind of say that we don't want the devices to communicate to the server, because this server could be very far, right? We want them to be able to communicate actually, within proximity, right? Instead of communicating to the server, because the server is really far from you, so you would waste a lot of power just to reach the server, right? And then you have to do it, across multiple iterations, so you would drain your battery before you can even train your model. So we came up with this idea to really solve federated learning now in a completely decentralized manner. So think of it as a graph, right? It's a graph that now you have a bunch of workers here, and you want them to communicate really within proximity. So we took this approach and we divided our network in terms of groups. Think of them as clusters, right? You have two clusters here, and then of course, once you have identified these clusters, every worker here, right, will communicate just with two, right? You can see these two neighbors here, and this one is the same. So in other words, you can solve the same problem as before, but now instead of having this kind of global model here, right, you impose the fact that my local model must be equal to the same model of my neighbor, right? And then we can use mathematical techniques here. In this case, we use this nice framework of ADMM, right? Alternative direction of method of multiplier. And we call it G for group aided, because here we're talking about groups. In this case, we have two groups. So essentially, this is a primal dual technique, where now every worker here, as you can see here, has to update its own primal, right? Then communicate those primals to the corresponding devices in the other group. Then they receive the model, then they update their own model and also the dual variable, and then communicate it back and forth between these two workers. This is essentially what we did. I mean, very simple idea, right? The difficult part here essentially was in terms of proving convergence of the algorithm, because in machine learning you could be interested either in just applying it without being interested in convergence proofs. This type of work, because we were kind of interested in journal machine learning research, we had to not only propose an algorithm, but make sure it does converge. So that's actually what we did, right? Now, if you want to plot results, you could, of course, look at many metrics, but here we were interested in the kind of test accuracy or objective error as the number of iterations and considering number of baselines, right? So this is a gradient descent. Then there is this, there are many here. There is this lazily aggregated descent, meaning that the device doesn't communicate always its model. It waits after a certain time, or it waits until the model is above a given threshold. And then our approach is really here. So as you can see, I mean, the performance gain is huge, right? Once you go from a parameter server, right, to a fully distributed setting, where now instead of talking to the server, I just talk to my neighbors, and then this propagates until we reach consensus on a given model, right? This was done, by the way, for a linear regression, but you could also think of doing this from a static setting, right, to a dynamic setting. So a dynamic setting here, I'm letting the devices to choose at different iterations, different set of neighbors, because let's say this graph here is not fixed, but changes over time. We could still show that actually asymptotically, we can converge to the same optimal solution as a static case, of course, pending some assumptions which are reasonable. But yeah, so again, just to show you the difference between static and dynamic. An important aspect here, I was talking to you about this idea of, the problem of non-AIDness. So once you use this framework of ADMM, there is this penalty term here, which hopefully you can see this row here, right? Which actually refers to a penalty of the consensus. Meaning, again, if some devices have more data than others, or maybe they have labels from certain classes that others don't have, therefore, there's a penalty, meaning that there is a problem actually, right? So, and you can see the impact of this row is pretty significant actually. Here, when you go from row equal 3 to row equal 7, there is actually even orders of magnitude differences. But again, here we were able to kind of mathematically capture that essence, right, via this model. Okay. Now, something very natural in this type of works is to look at model quantization. Why? Because now the idea is, instead of communicating to you a full model, think of it as a 32 bits, right? Can I ask the question now, can I actually compress this to 1 bit, 2 bits, 4 bits, right? And still maintain the same accuracy, or maybe lose a little bit. That's essentially what you see here. So we apply this kind of stochastic quantizer where we have your original model, which is n-quantized. And then what you're trying to do is to kind of come up with the quantization range, right, and the resolution, and then try to play with this kind of resolution so as to now, of course, again, we were interested here in the convergence of the algorithm, because once you quantize a model, you are propagating errors, right, from different workers here or devices to the others, and therefore you need to make sure actually that this quantization leads to an unbiased estimator and then stays within bound of the global optimum. That's essentially what we did. In terms of performance, what you can see here, again, this is a loss number of communication rounds for a gradient descent. This is quantized gradient descent with 2 bits, and this is our approach, JDMM, and the quantized version of it with 2 bits. You can see here actually there is no loss of accuracy whatsoever. The same accuracy is reached whether you use 32 bits or 2 bits. So this speaks a lot about the fact that we are wasting a lot of resources when we communicate the full model. And actually the more interesting part is actually, of course, the total number of transmitted bits is much, much lower once you go from the full model here, 32 bits to 2 bits, right? Why? Because again, you are just compressing, while not sacrificing any accuracy. This is very interesting. That's actually what's also reflected here. Now, some people may be also interested and saying, okay, but actually when you started, you only consider one type of graph, right? This is a chain topology here. This is a chain, right? Now, can you relax this? Answer is yes. That's what we try to do here. We went for a different type of graphs referred to as bipartite graphs. So bipartite graph meaning that now if you have 2 groups, right? then any device can communicate with any number of workers, right? So here it was maybe 2, here you can have 3, 4, 5, right? And then again, the analysis carries over. We also look at, and this is, by the way, referred to generalized group ADMM, right? And then you can extend this further by now saying, okay, I don't want to be communicating my model at every time t, either quantize or unquantized. I want to be able to use some sort of criterion when I only communicate when I have something useful to communicate, in other words, right? So this is the idea of censoring, okay, which says actually that you want to communicate, okay, if this is the quantized model, right, minus this Q hat here, this is basically the sequence of previous models, right? If this difference is larger than a given threshold, then you transmit, okay? That's essentially the idea we did. And actually this brings even more results, I mean more performance gains, because we compound now. We're compounding gains from quantization, gains from communicating only when the model has a useful update to make, right? And the sparsity topology, because here again, I am not in the star topology, which is a federated learning idea, but in a fully distributed setting. So you see here the gains go from here to here, which is pretty significant actually, right? This is what you see here. Now, of course, people again may be interested in the aspect of graph connectivity. So when you go from a dense setting here, right, dense graph to a sparse graph, this is very interesting because, of course, there are trade-offs here. So having a dense graph is good for conversions, meaning that you can average very fast, right? You have many neighbors to average from, but of course you pay a price in maybe, you know, convergence takes more time, okay? Whereas now if you have a sparser graph, okay, then, you know, you could, you know, you could receive only from few workers. So if you are limited in bandwidth, this is great, right? But then you may pay a price again in conversions. So this is a bit what you see here. This is the loss again and versus number of communication rounds. And of course, we want to go this way, right? This is the idea here. But this is not the full story, because now we need to also look at the, if you look at robustness, right? So this is great for robustness, because now even if one edge is dropped, no problem. You can still, right, aggregate from the other neighbors. Here, no. Here is great to have sparsity, but if this link now, you know, is blocked or for whatever reason, then you're in trouble, right? You're no longer robust. So this is again a trade-off. So we shouldn't look into only accuracy versus convergence, but also you need to take into account in terms of convergence, communication efficiency, and robustness, right? And of course, energy. This is something that is not really much looked at. This is why most of the papers only report test accuracy, but they don't really report the energy bill to train a given model. In any case, so of course now you could now take whatever I have presented to you thus far and extend it towards many different avenues. So you could now, of course, take any type of topology, static, time varying. Something we have not looked at is a non-convex setting. So all our problems were for the convex setting, because again, the proof is easier. But obviously now if you talk about DNN and deep neural networks, you essentially have a non-convex problem. But so again, worth trying. Most of the works are dealing only with first order methods, but we know that second order methods are actually much better because they can capture the landscape of the loss function, meaning can converge even faster, right? Then you have, of course, Bayesian learning, which is actually even more important nowadays, because once you're interested in uncertainty quantification, you need to use techniques such as Bayesian learning, because if you don't do that, you probably end up overfitting, meaning that if you don't use this technique, you would provide me with a test accuracy, but you probably will be overconfident, meaning that that test accuracy is completely bogus, right? Therefore, what you need to do is give me some sort of uncertainty quantification, which will be the variance of your prediction or some other metrics, right? Reinforcement learning obviously is a very interesting, I mean, sometimes it's the only way because you don't have labels, right? So you need to learn by interacting with the environment. So of course, reinforcement learning is a very important tool. Now actually what I'm gonna do is switch a bit gears, and I'm gonna talk to you about a very interesting marriage or co-design between these two, right? This machine learning and wireless communication, because sometimes people use this word co-design, but they just use it actually, or they abuse its usage. So what I'm talking about here essentially are two distinctions. The first one is what we call digital federated learning. This is where all the papers today are focused. And here again, so now we are in a wireless setting. So now if you have million devices, and this is the setting of federated learning, trying to communicate with a server, this is a problem because now you don't have enough bandwidth, right? You don't have enough resources. Therefore, you need to either get more bandwidth, not a good idea, or you need to schedule maybe, okay, and now I just schedule a few users instead of 1 million. It's essentially a difficult problem to do. But what this says here is that you're trying to avoid interference, right? Now, what we're trying to do now is completely flip this paradigm and think about a kind of analog federated learning, where now the idea is actually the more devices I get, the better. And why so? Is because now in federated learning, the server does not want to decode every single update from or model from the worker. What it wants is the average. And therefore now, if you let actually the channel act as a natural multiple access aggregator, you can actually in one shot aggregate the entire models, as opposed to doing it with this digital approach, which says actually here that the more workers you get, the more devices you get, the performance goes down. Why? Because you are limited in interference and resources. So essentially here, this is different. This is, I want to have interference. I want to exploit it to kind of modulate the signals, the amplitude of the signal, to average them in one shot at the server. And this is great because now you can even obtain actually privacy for free. You have to know that privacy, I mean, in machine learning community, for them essentially is about maybe blurring out the gradient, meaning adding some noise, but that takes a cost, right? Here, you're not doing that. The channel is providing you privacy for free. So why not looking at this approach? And that's what we did. So essentially, we mathematically model this idea here, which you can see here. This is an analog federated ADMM compared to the digital one. So essentially, what you see here mathematically is very simple, right? You just take the digital approach here, right? This is the augmented Lagrangian, by the way, for those who didn't follow before, right? You just write this down. It's very simple. This is the penalty of the disagreement or the consensus, right? And you write down this is a primal update, this is a dual update. Now, what you want to do now in the analog case is really to jointly encode the model and the channel, right? This is the difference between this constraint here, right? And in doing so, you rewrite again your augmented Lagrangian. And of course, now you need to come up with new updates for your primal and a dual update. And then, of course, again, still prove that this converge, right? That's essentially what we did. And now the results are actually even more interesting, okay? So what you see here, I'm going to maybe skip some of the details here for lack of time. So now I want to take an image classification task, okay? I'm plotting here the test accuracy, number of communication uploads, right? And I'm comparing here, this is the digital baseline, okay? This is all the analog baseline. So you can see here immediately that the digital takes much more time to converge, number one. Number two, the analog one is extremely fast. Look at this, few communication rounds already converge, okay? Why? Again, one slot, we can aggregate, okay? Now what we try to do is to be a little bit nice with the digital baseline by giving it 10 times, what is it here? Yeah, 10 times more, okay. 10 times more resources, okay. Here is 10 times more resources, and this is where you can see it's still struggling even to match the performance of the analog. It does reach it perhaps after, you know, maybe it's here, maybe, right? Maybe 4,000 uploads, right? Communication uploads, whereas the analog was extremely fast. This is communication efficiency. Now, energy efficiency is even more interesting because now in the low SNR regime, this is a sensor, maybe local sensor, right? You can see here, so this is the performance of the analog in red. This is digital. So the digital has to have a very high SNR, 20, to really start to have a very good performance in terms of accuracy. Whereas the analog is completely oblivious to the SNR. This is an extremely powerful result in some sense because, okay, why don't go for analog? And this is the same result, essentially just in terms of scalability. So as you increase the number of workers, the performance analog, you know, still the same to reach a given target. Whereas, you know, you need more resources. This is essentially showing you that This is a scaling of the number of bandwidth that you need to do to ensure, I think the accuracy here was 0.9, right? Whereas look at the analog, right? I mean, it's almost linear. We also did some privacy analysis here, and maybe I'll skip this just to mention that we also can show that, you know, this algorithm is really privacy preserving. I mean, in other words, the server is not able to invert the model of the worker and know basically which worker has really, you know, contributed to the model update. We don't want to do that because of privacy issues. All right. Different type of work also is now, what if now, okay, I want to train. Now I'm back a little bit to the centralized case of Google, but now when I train a model, I don't want to train with the private data of the workers. I need to make sure somehow that by doing a smart combination, smart aggregation of the labels and the data of the workers, they aggregate in some sense so as that they are blurred out. So we call this a mix-up technique. And this is what the server will use not to train a model. Okay, this is again different than federated learning. Here, the burden, the cost is at the server. The device don't do anything. Okay, is the server? I mean, they do something in the sense that they have to tune the transmit power such that the received power here, as you can see, right? Sum of power, channel, labeled, and the data and the noise, right? Such a way that it's blurred at the server. That's essentially what we did. And we did some analysis because here we were interested in this differential privacy characterization, meaning test accuracy versus privacy, right? So if you want to ensure privacy, well, you have to pay a price in accuracy. If you're not interested so much in privacy, okay, your accuracy increases. This is a bit what you can see here, right? So small epsilon means very high level of privacy, right? And this is why the accuracy is pretty low, right? As you relax this privacy constraint, you can see here you can go from 74 to 95, but I mean across a wide range of number of workers, right, or number of scheduled even workers. This is essentially the idea in short. Now, you can also push these ideas in the realm of control. So as you know, of course, we talk about cyber physical systems, you know, remote control, perhaps from a server or across multiple robots in a factory. Essentially, how can we, you know, push down this idea of privacy preserving model training, even in the control space? And that's actually what we did here. This is a very classical kind of setting where we have, say, a source, a destination, maybe it's a rescue mission, and you want to dispatch a lot of drones, right, to carry that task. Now, this is a fully autonomous setting in the sense that the drones now have to communicate. I mean, they have to optimize their travel time as fast as possible. They have an energy budget, and they need to avoid colliding with the other drones, right? And then, of course, we even added some perturbation of the wind here, right? So now, of course, you can massage this in a different way, but here we adopted this idea of kind of mean field game theory, which is allowing us essentially to decompose this problem, because this is a highly coupled problem, right, between all these agents towards one agent and then a population of other agents. So for people who are familiar with the flock of birds, that's essentially the same idea, right? As you increase the number of birds or drones, you're able to decouple this control problem. So this is how we would write it mathematically anyways, right? Minimizing cost function, which takes into account, again, the travel time, motion energy, and collision avoidance. Now, if you want to really solve this, this is very difficult, because now what you need to do is write down two partially differential equations. First one is what we refer to as Hamiltonian Jacobi-Balaban equation, which is essentially finding the optimal control parameter, right, to go from point A to point B. So again, this is very difficult. This is why I'm putting it even here, so you don't have to understand it. Other than this equation here is difficult to solve, number one. Number two, the other one, which is calculating the population dynamics here, right? This is kind of the average velocity of the entire drone, right, or flock of drone. This is also another partial differential equation. So to solving this is very difficult. So essentially what you can do, of course, is to maybe, you know, relax the problem or maybe revise your hypothesis. But here we use machine learning. So we approximated the first equation as using a neural network, and the second one using a neural network. And we applied principles of federated learning. And actually, the results were very, very interesting. So here what you can see, this is a number of baselines. So this is when the drones communicate their states at every time t. This is when they do it at every 100 time t. And this is our idea, meaning don't do it. Do it once and then run these two partially differential equations, and then you will be much better in some sense. How better? Well, here we were interested in the trajectories of these drones. We have 25, right? This is time, 30 seconds, 60 seconds, 90 seconds, 200 seconds. And what you can see, this is the trajectory, by the way, of the drones. And I need you to pay attention to this red stars here. This corresponds to collisions, right? And that's what we don't want, right? So you can see these collisions happen in the first baseline, second baseline, but not in ours. In ours, this is the trajectory of the drone, right? As you can see here, if you compare these two here, we have 0 collisions, but we are paying a price in terms of the drone has to really take a wider turn before reaching its destination. That's essentially what we did in this work. Okay, and these are the dynamics of the parameters of the training. Now, of course, there are a number of questions here we still need to look at. For example, the robustness, right? Because essentially here we are just approximating the function. So now, of course, you have this, generalization to out of distribution. If you train on one distribution and then the test distribution is totally different, this completely fails, right? All right, so now I'm going to move to the second family of algorithms I told you before, this federated distillation. So this is a very nice idea in the sense that it outperforms federated learning. Why? Because in federated learning, if you recall with me, I was telling you that we need to use the entire model parameters. Here, no. Here we only communicate the logits, which are this kind of pictured here. For those who don't know what logit is, if this is your input, right, an image, you feed it to a neural network, then you get a kind of a distribution or a, here is a cat and dog, for example, 80% is a cat, 20% is a dog, right? And then you push this to a ReLU or other softmax, maybe output, and then you use those values, 0, 1. This is a cat, this is a dog. The problem is, what we want to do is not use the fact that this is a cat or a dog, but I need a bit more information, right? And this information is really what is referred to as the logit. And this is now what is now communicated to the server. And then the server will just, again, aggregate now the logits, right? And then use this kind of signal to train the student. So we have a teacher and a student. The teacher somehow is all these devices who are uploading the logit. And then what you do, this is where the word distillation comes from, right? You distill this knowledge of the teacher towards the student. So the student here has his own neural network and is trying to match the performance of the teacher. That's essentially the idea. Now, mathematically, this is very simple. If you forget this term now, this is the stochastic gradient descent. Weight update, worker k, iteration I is wk minus learning rate. This is the gradient loss, okay? That's it. Now what we're doing, we're adding this term here. What is this term? This term essentially captures the difference of prediction between the teacher and the student. If this prediction is the same, great, you're on the right track. If this is wide, okay, then you add this as a regularizer in your stochastic gradient descent update. That's essentially what we did. So a very simple tweak. This is the same thing. But you can see here the performance here. If you compare now federated learning versus federated distillation, right? In terms of accuracy, but also communication. So you have a trade-off here. Communication accuracy trade-off. Here is the communication cost, right? So, and this is the test accuracy. So you can see here, of course, federated learning has higher accuracy, but it's significantly high costs, right? Why? Larger models. Whereas federated distillation has a very, very low communication cost. I mean, this is like 4 orders of magnitude, massive, right? The downside here, of course, is that we have lower test accuracy, right? This is the bump in performance. So again, depending what's your budget, communication or accuracy, then you need to trade off and choose your point. But we can actually even do better, because now the conclusion of this work is federated distillation is great in the uplink, because this is typically where you are constrained. And on the downlink, maybe you want to use now federated learning. So we came up with this nice hybrid of, we call it FLD, I think. Yeah, so federated learning, federated distillation in the uplink and federated learning in the downlink. And we compare the performance in terms of if you have symmetric channel or asymmetric channel. essentially to capture the fact that, yeah, maybe the uplink is worse than the downlink, which is the case in ways, right? And you can see here actually that the accuracy is much better when we compose both, I mean, the hybrid, federated learning plus federated distillation. So you have a much better accuracy than if you just use only federated distillation. So again, you can, of course, in the symmetric case, uplink, downlink are the same, so not an issue. But we were interested really in this asymmetric when the uplink is poor compared to the downlink. All right, very good. And now, so now I talked about federated learning, all right, federated distillation. There is another technique actually, which is referred to as split learning, which is also kind of getting a lot of attention now. So in federated learning, remember that you're learning one global model is here, right? Between the device, there are many devices, of course, and a base station. Here, the idea of split learning is I'm taking this kind of model and I'm taking a knife and I'm dividing this model in terms of a model sitting at the device and a model sitting at the server. And this is called split learning because, as the word says, you're splitting the neural network. So now, of course, how do you split it, right? Between device and a server as a function of accuracy, communication costs, and of course the task that you have in hand. So this is the idea essentially of split learning, right? So now this is among multiple devices or clients. So you need to, again, I mean, so what you do, I mean, how does this work? So actually what you do, of course, you have your data here, right? You run a few steps of maybe gradient descent, and then then you smash your layers, meaning you cut it here. And then what you do here, because you're limited in maybe compute constraints, right? Then you communicate this forward tensor to the server, and you're asking the server, hey, please continue training for me, continue running SGD steps for me because I'm tired or because I don't have enough resources. The server does it for you without even knowing the labels. He doesn't have the label, right? So then he just finishes the work for you and then back propagates these values, and then you can continue locally, and then find maybe you train a model in a hospital. Then you can maximize your maybe test accuracy or something, right? That's essentially how it works, and it's it's more privacy preserving than federated learning. Why? Is because here you don't have one model, you have multiple models, right? Whereas in federated learning, one global model is a target, right? So this is where kind of it's less privacy preserving, because even though federated learning is saying that it's not using raw data to train, there have been some works that show that you can actually do what they call reconstruction attacks, meaning from the model or the gradient be able to infer the raw data, right? Anyways, and then of course there are many flavors of split learning. You have one is here, right? You split again. The labels are sitting at the server, right? Then you have maybe the medical case. You have hospitals, so you cannot share the label of the data. I mean the label of the patients, right? So this is the same as the previous slide. Continue training for me, and then you have a U-turn here. Tag labels are here. This is multitask. Maybe you have multitask kind of split learning, right? So this is a bit the idea. Okay. All right. So what we did in our case, actually, we use this technique in the context of wireless blockage prediction. This is actually a very nice problem. You have a base station here, right? And then you have a user, and then you have a blocker blocking the signal. If you wanna plot this in terms of received signal strength, it's very straightforward. You have these dips in performance, right? As soon as you have a blocker, performance drops, right? So now what we were interested in is essentially predicting this blockage before they happen, not after, okay? So now how can you do that? You could do it either using, of course, signals, channel state information from the base station, right? And try to learn a neural model, right? Using any type of architecture to help you train a model. The problem with this is actually, even if you have 1 billion points, sometimes it's not enough. But why? Because you don't have enough statistical significance in your signal so as to tell you, hey, there is a blocker coming. What you could do now, and that's what we did, we leveraged cameras. We said, okay, you have a base station, and then you have also a camera on the base station or somewhere else on the wall. And this camera right now is taking images of the environment, meaning it's able now to locate a blocker and even predict its trajectory. And then, of course, you can predict when this blocker actually will block your signal. That's essentially what we did. So in terms of machine learning jargon, we use two modalities. One is the images, right? Captured by the camera. You feed this to a CNN, you get your feature vector, feature maps, and then you communicate them to the base station. The base station does the same based on its RF signals, right? And then it feeds this now again, it does some processing. And then it feeds this to now the inputs of a recurrent neural network, which gets as an input the feature vector from the camera, and then the feature vector from the base station. And then you try to now jointly learn a model to predict the blockage. That's essentially what we did. And we, again, plotting some tests. This is a root mean square error. This is a communication cost. So, and also we try to play a little bit with the filter dimensions, because for some people, maybe they are concerned with privacy. Okay, no problem. We can actually compress this filter going from 1 by 1 to 4 to 40 by 40, and I can actually even use kind of a white, black, gray kind of pixel to help me predict in the RF domain. Because now remember, you have data in the RF domain, and you're trying to also leverage the camera images, right? And what you can see here, I mean, again, very nice trade-off. So again, here you can have high performance is here. Actually, the most optimal is 4:4. This kind of resolution. Why? Because you trade off between communication and accuracy. Remember, if you don't filter too much, you have high resolution image, you pay a price in bandwidth, because you have to communicate that to the base station, right? If you compress too much, you lose information. So you need something in between. Turns out something in between is really 4:4. Okay, this is the optimization part. Now, of course, even if you use 1 pixel, 40 by 40, you can actually outperform the RF. So RF is this one here, right? No camera images used. If you just use 1 bit feedback, look at this, you can actually get a better performance compared to the RF. So again, this is very interesting. And we try to look at this also when we distribute actually cameras, right? Instead of going from 2 cameras to, say, multiple cameras. Now once you do that, actually, you have a number of problems that you need to focus on, meaning, okay, if cameras have different compute power, so you have this heterogeneous problem again, or non-AIDness. So if you use federated learning in this setting, it will hurt the performance, because you cannot average models coming from different cameras with different frame per second. It fails. And actually, that's what we actually demonstrated in this result here, comparing RF-only, camera-based, and federated learning, right? I'm gonna maybe skip the detail here for sake of time. But yeah, this is essentially what we did here, using, again, this idea of split learning and mix-up. Mix-up is another kind of nice technique. Mix-up is about data augmentation. Say you have data and labels from different modalities, you can mix them up. So you can mix them up either in the raw domain, at the level of the pixels, or you can mix them up at the level of the inner representation, or you can even mix them at the level of the label. This is a very kind of interesting idea, and we exploit it here in this idea of blockage prediction when you have multiple cameras. And these settings now are very popular, even in beyond 5G setting, in a factory. You deploy cameras and you want to detect blockage, or you want to image the environment. This is a very, very useful tool for that. And of course, there's more work to be done here. All right, I think this brings me to the end actually of my talk. So yeah, I hope that you got a good overview of what we mean by edge AI over wireless, because here my interest was really how to bridge these two disciplines. This is a very, very hot area actually. Perhaps it's top 2, top 1 topics in communication society. A lot of publications every week, every day. But in fact, there's a lot of work to be done, because essentially we maybe have jumped to this topic and forgot a number of techniques, a number of things. For example, robustness. All the current federated learning techniques are probably not robust. And I told you why. One reason is because it does not quantify uncertainty, meaning it does not know when it does not know. Okay, so it's overconfident. Then you have this notion of generalization. This is, of course, the big goal of machine learning, essentially the ability to generalize not within the same distribution, because that's kind of easy, right? That's interpolation, but extrapolate, being able to go in a totally different environment where you have zero data and be able to operate by leveraging, exploiting this knowledge that you have acquired across multiple Okay. And of course, energy. This is a big issue nowadays, of course, with the climate change, and we need to characterize the energy bill, because there's no point to have 99% accuracy if you are using all the forests of Africa, of the world, to train those models. It's completely ridiculous, right? Therefore, we need maybe to now reduce our accuracy to save energy. And again, this means that we need to incorporate in our system design and even in our mathematical formulation accuracy and energy constraint, right? And then in my final word here, really the next 5-10 years, no doubt about that, essentially will again be the marriage of these two disciplines of communication and machine learning, but actually both of them suffer from this idea of learning statistical correlations. Because today machine learning is simply learning patterns from data, right? Statistical correlations. However, that's not the way humans learn, essentially, right? It turns out in communication also there's a nice work now starting to happen in what is called semantic communication, right? Or post-channel communication. Because also in communication theory, it's a theory of statistical description of information, okay? You're trying to look for the probability of occurrence of messages. So rare messages, you encode them with more bits. Very common messages, well, you basically don't even transmit them perhaps. But that theory completely removed structure, context, semantics, and therefore you can see there is a very nice, these two suffer from the same problem. Now, if you are able to combine these two, meaning semantic communication and a different type of machine learning referred to as system 2 machine learning, for those who know this word, this is extremely promising for both communication field and also machine learning. And with that, thank you very much. Happy to take maybe a few questions. Let me just go back to my oops, to see the camera. Or is it? Yeah, maybe here.
Yeah. Thank you, Professor Bennis. It was really interesting, and so it was a very interesting presentation with lots of concepts and lots of new information. So thank you again very much. And I don't know if we can have any questions here in the audience.
Some questions maybe on the chat, but yeah.
Yes. So I'll read it really.
I can do that, no problem.
Okay, go ahead.
Yeah. So research on distributed machine learning has great significance. In recent years, federated learning is an important development, sure, compared to traditional, it pays more attention to data privacy. However, my question is why the existing federated learning does not support heterogeneous model? No, it actually does, right? So the vanilla federated learning version 2017 didn't, but nowadays you have a lot of works looking at non-IIDness. So we have also in my group a number of works in that. Essentially, yes, you need to essentially capture that non-IIDness via either imposing a cost, like in our case, we have this penalty disagreement between workers. Why? Because they have different data distribution, but you can do it in different way. You can impose a different type of regularization. There are some works also that did this. There's a nice algorithm called FedPack, I think, if I don't forget the word. You can also do clustering. You could do a lot of things to address this non-IIDness. But of course, maybe the other question to ask is, how do you know in advance that the data is non-IID? This is something that is not really looked at, right? Here we are making the assumption, I know it is IID, I know it is non-IID, but somehow we need to estimate that before, right? Or as we train. This is something also kind of important if we want to do it in a real world setting, yeah? Which means, again, you pay a cost now to know whether you are in an IID or non-IID setting. But again, it's kind of interesting, right? But what I advise you to do is really, because it's easy to run the algorithm and plot test accuracy. But what I didn't do today, for example, is to show you the guts of the algorithm. And you can show actually if you plot, just if you take two workers and plot theta1, theta2, or W1, W2, and track the trajectory, okay, of worker 1, worker 2, average them, because federated learning tells you just do W1 plus W2. If it's non-IID, you will see it completely drifts. It either goes towards the worker 1 or worker 2. Because if they were IID, they have to go exactly right in the point or the line between W1 and W2. So it's kind of nice to show it even visually in the geometric space of just W1, W2, and plot the iteration steps, right? So you will see it's a very straightforward but interesting observation.
Okay, thank you. I think the answer was clear. Is there any follow-up questions? So in the meanwhile, I have a small question. So as far as I understood, your presentation was about demonstrating the limitation of classical machine learning in the context of wireless communications, given that most devices are limited in terms of bandwidth, latency, storage, maybe also. So at some point you mentioned that we were trying to shift from communicating with a server that will do all the work for us to maybe communicating with the next edge or the next node. So my question is, what criteria does a device have to choose which edge, which neighboring edge it will contact?
Yeah, very good question. Yeah. So essentially, so the criteria to in the centralized setting or the star topology, right? It's very easy because you know who is acting as a server. You know who's acting as model aggregator. In the fully distributed setting, is very difficult because you don't know, right? So you need to discover that part. But just to also which device are going to connect to? Is it the one that is nearby? But actually his model is completely useless for you, right? He needs to keep iterating his model, or is the guy who's a bit farther from you, so he's harder to reach in terms of power, but that's the guy that you want to get your update from, right? So there are many criteria you can think of. We haven't looked at that for now, but of course if people want to build on our work is this. What's the criteria? Can you encode both the SNR or SINR or path loss or distance with the model updates, right? And come up with a new, actually call it even censoring strategy, right? Which picks up the right device for you at the right time based on a combination of SNR again, maybe model updates, right? And that's what should be done. Yeah, that's for sure an interesting open work, right? But I mean, you can really easily extend the framework if you want. That should be possible. But then it means also if you want to be a bit more technical, you need to exploit the structure of the graph, right? Maybe you need to look for, because you need to make sure the graph is connected. Because if it's disconnected, what you end up with is two separate models. So even works in graph theory and learning algebraic connectivity of a graph, right, are very related. So if you can combine graph theory, again, machine learning and communication, that's a very nice framework.
Okay, and have you implemented this approach, these algorithms that you proposed? Have you implemented it either? No? Okay.
No, we haven't. Yeah.
Okay.
We haven't, but they are always asked because they are the kind of obvious ones. Because again, our departure was really to focus on the mathematics part, meaning proving algorithms converge without this kind of things. It's quite difficult, of course. Now, if you just want to apply, you can do it right away. But the question would be, okay, can you prove that converges? Then, okay, maybe not. It depends, right? But I think any student listening to us now can really jump on this problem and can easily publish a paper. Yeah.
Okay, thank you. Yeah, we have a question in the audience.
First of all, I'd like to thank all the Babo faces in order to be technically speaking with the event, which has allowed to us to have what we say to keep in touch with these currency issues, which is data, big data, and digital era. I'd like to wonder if you know, Professor, with you, when you have concluded with the fact that we are going to deal with what you have called the semantic communication.
Thank you. Yeah.
I don't know with
I cannot hear you very well right now, but it's just
going to deal with the new semantic communication, and as a billionaire in this what we say square of digital, and the graduate of the Information Science School, I like to wonder with you whether you like to say that the 1.0, 2.0 and the semantic web and l'Internet des objets or the Internet of Things, which will be the 4.0 or 4.0, we are what we say to revisit or redo with what we see what the data miner and the text mining who have what we say the occasion to do in the what we say the 23rd millénaire, dans ce début du 3e millénaire. Est-ce que vous êtes là encore en train de dire je suis désolé, je ne suis pas très doué en anglais?
C'est pas grave, vous pouvez la poser en français, c'est bon.
Durant les deux décennies derrière, c'est-à-dire en termes de métadonnées, le texte, le web sémantique or semantic web, or you are talking about something, what we say, the new era or the new generation of semantic web that we have, what we say, known in these 2 decades. Thank you.
Thank you. I think, yeah.
I could get the point.
Mm-hmm.
So a very good question. So my last comment there on the slide is basically, so people working in web, for sure, they deal with this idea of semantic web, knowledge graphs. Actually, that's a very, very interesting component and research, which we have not actually exploited in machine learning, neither in communication. So communication today is really based on statistical correlation. To the receiver, you get X hat, and then you want to make sure X equals X hat. That's what we have been living with since 1948, the paper of Shannon. Now people are waking up a little bit and saying, actually, that's not the best way to communicate. Why? Because humans do not do X equals X hat. Humans, like me now, I was able to decode your question, is because I'm able to infer, predict the communication intent of your speech. I didn't try to decode every single syllable, right, or word you told me. I'm able to really infer your intent. That's semantic communication, right? So now we need to bring that part to communication to make it much more efficient, much more smarter, much more robust. Now in machine learning, they suffer from the same problem. As I told you before, if you're familiar with this NLP, natural language processing, is great, and there are a lot of news about it in the news, but it's actually just learning from a huge corpus of data, and it trains and it be able to answer, even converse with you. You can actually always trick it, asking some questions, because actually it does not understand. It's able to mimic what it has seen in the training data. This is why now there is a difference between NLP and NLU. NLU is natural language understanding. So this word, understanding, is what we don't have today in machine learning, is the same word which we don't have in communication. If we are able to accomplish this dream or vision, then machines can communicate, they can communicate with you, they can help you, assist you, but this is a 20 years journey, because it's a very difficult problem. I mean, my group just started working on this. It's fascinating work, because, research, because you need multiple disciplines, you see. You have information theory, machine learning, that's not enough. You need to look at linguistics, you need to look at cognitive science, you need to look at psychology. Because again, the ultimate goal for me, but I think for everybody, should be that we need to be able to learn from ourselves, the humans, because we are very smart, right? And use that ability and bake it in networks. If we do that, that's extremely powerful in many reasons, of course. Energy, again, sustainability, all these keywords we hear about. That's the only way somehow, right? Because today, unfortunately, the way we solve problems for engineers is the more the better. I have a problem here. Okay, no problem. Let me deploy more base stations. Let me add more frequency bands. That's the wrong approach. Now, maybe with semantic communication, we can reverse this trend by being even more intelligent. How? Yes, again, we need to really go back to research. So this is also a very good topic for our students, because we are at the very beginning of it, you see. If you want to do a PhD in a topic which has been there for a while, you will have almost no contribution, right? Maybe it makes sense to start from these new topics and really, try to be as multidisciplinary as possible. That's my recommendation also to everybody, right? And try to make progress there. Hopefully, I answered your question.
Thank you. You did, yes. We'll take one last question, if you allow us, Professor Bennis. Okay. So, in addition to privacy, efficiency gains and lower resource requirements in distributed training reduce the environmental impact of training large machine learning models. Did you think or work to the introduction of a practical and reliable distillation technique for heterogeneous models and for low-resource clients? Because the person who asks thinks that it's a step towards more broadly enabling collaborative, privacy-preserving, and efficient decentralized learning.
Yeah, sure. So essentially what she's maybe saying, yeah, you can take our federated distillation technique and you can extend it in a number of ways. One of them is to make them more reliable, which we have not done. Number two is to take into account the resource constraints, and we only focus on communication and accuracy. We didn't address energy. We didn't address reliability. So this is a clearly open problem. And then you can also, expand it towards more distributed graphs. We only did server, right? So again, yeah, definitely worth investigating. And again, the same questions will pose, meaning, how do you choose your device? Which one? Nearby, farther? Maybe this guy is, has zero value for me, so I need to look for the device in the cluster which has more value. I mean, this is an open problem for sure.
Okay.
So
thank you.
I call this problem, by the way, just to summarize. I mean, these are all low-hanging fruits. You see, so really, it's very important to jump on them as fast as possible because these are what everybody else is thinking about, right?
Exactly.
So.
Yeah, it's an opportunity for research.
Absolutely.
So thank you very much, Professor Bennis. It's been enlightening to assist to this keynote presentation. I'm sure our students have and the PhD candidates have learned a lot from your presentation, and looking forward to attending another presentation of yours maybe soon. Thank you.
Thank you very much. Thank you very much again, and assalamu alaikum and all the best. Bye for now.
So I think we'll have a small break, 10 minutes maybe. Okay, and we'll continue with our second session.